Great, it worked. Sorry, but that's the thing about programming. Once you start, you can really get caught up in it. Programming can be a lot of fun. If you're watching this video, you've probably had some questions about programming. Questions like, what is it? And how do you program in Turbo Pascal? Well, the first of these questions is easy to answer. If knowledge is power, then knowledge of programming is power over the computer. Because by programming, you can make the computer do exactly what you want it to do. And that's what this video is all about. I'm Zach Erlacher from Borland International, and for the next hour and a half, we're going to take a quick tour of the world of programming using Turbo Pascal as our vehicle. Turbo Pascal has a reputation for being a very fast and easy to use structured language. And in your package, we've included a complete version of Turbo Pascal. We begin by introducing you to Turbo Pascal's integrated development environment. You'll start to create your own programs right in the first lesson. Then we'll move on to the main parts of the language. We'll discuss subjects like variables and data types, expressions and operators, control statements, input and output, or I/O, data structures, functions and procedures. We'll work our way right up to today's state-of-the-art programming technique, object-oriented programming. Before we start, make sure that Turbo Pascal is properly installed on your system. If it's not, the self-teaching guide explains how to do it. A knowledge of Turbo Pascal puts you in the driver's seat. All you have to do is start it up and get ready to ride. After all, we don't call it Turbo Pascal for nothing. That was a quick ride, and now we're ready to roll right into Turbo Pascal. If you don't have Turbo Pascal running, start it by typing Turbo at the command line prompt. We'll begin with a quick tour of the Integrated Development Environment. The Integrated Development Environment, or IDE, includes all the tools you need to write, edit, compile, and debug Pascal programs. A context-sensitive help system delivers the help you need whenever and wherever you need it. And you can access menus by means of a mouse or the keyboard with equal ease. As soon as you learn your way around the IDE, you're ready to begin programming. We'll cover some of the basics of programming, starting with a brief discussion of what we mean by structured programming. Then we'll move on to writing, compiling, and running a program that introduces you to important programming concepts like input and output, loops, and decision branches. When you start up Turbo Pascal, the program comes up in the editor screen that you now see. The editor is part of the integrated development environment, as shown in this diagram. It's used for writing and editing our Pascal programs. It also acts as a sort of gateway to the other IDE tools, including the compiler and the debugger. The compiler is the part of the IDE that translates the Pascal language that humans understand into the machine language that the computer understands. The debugger is a powerful tool that gives you a close look at the inner workings of your program while it's running. And it works with the editor to allow you to interactively edit your programs while you debug them. This can be a real time saver. You can move around in the IDE either by using a mouse or the keyboard. If you want to use a mouse, just make sure your mouse driver is loaded before you start Turbo Pascal. To use a mouse, just move the cursor to the menu entry you want to select and click on it. If you don't have a mouse, no problem. The keyboard is just as easy to use. To select an option from the menu bar, just press the function key F10 to highlight the menu bar. For example, to open the File menu, press F10 to highlight the menu bar. Then press F, because that's the highlighted letter in the file entry. From here on, we'll be using the mouse to move around. But whether you're using the mouse or the keyboard, at the back of your book, you'll find an excellent section on keyboard shortcuts that you should be familiar with. Now we're ready to take a closer look at the IDE. Since the File menu is already open, we might as well start right there. The File menu provides commands and operations that let you manage the files you create in Turbo Pascal. These files can include, for example, source code and compiled code files, as well as program data files. The file management operations in the File menu allow you to create, open, rename, copy, save, and print files. This menu also provides a way to change working directories, the directories to which you automatically save things or from which you open new files. The File menu also has commands to launch a DOS shell and to exit. Notice that several of the operations shown in the File menu have 3 dots following their name. This means that when you select one of these options, a dialog box will open up. For example, let's see what happens when we select the Open command. The Open dialog appears on the screen. The dialog is automatically set to the current working directory as indicated in the status line at the bottom of the screen. At the top of the dialog is an input box into which we could type the name of a Pascal file that we want to open. And the center of the dialog contains a list box. This field contains a list of all the Pascal programs in the current working directory, as well as a list of all the other directories accessible from that directory. The cart file program appears in the list, and we can use the File menu to open it, like so. By the way, we'll be using this program occasionally through the rest of the lessons. Since we don't want to work on it now, all we have to do is close the window, and the file we opened disappears from the screen. Now let's visit the other menus of the IDE. The Edit menu gives us all the operations we need to deal with program text. This text is also known as source code. Operations available in the Edit menu allow us to cut, copy, and paste text in the source code file. The Search menu provides a number of operations that help you find and replace text in your program. If you've ever worked with a word processor, you're probably already familiar with these functions. They're helpful, for example, when you decide to make a change in your program that will affect it in many different places. The Run menu is where we'll go to run our programs after we successfully compile them. It's also the point at which we can start debugging our programs if they don't work correctly. The debugging functions accessible in the Run menu are Trace, Step Over, and Parameters. As you can see, the Parameters command is followed by 3 dots. That means that if we select it, a dialog will appear on the screen. Let's go ahead and give it a try. To find out more about this dialog box, we can use a little help. Terrific! Just the information I wanted. That's what we mean by context-sensitive help. You can always get help in Turbo Pascal by pressing the F1 key. Now, let's move on. The Compiler menu offers commands and options for compiling, making, and building a program. Most of the time, we'll use compile. Make and build are handy for larger programs, and you can read more about them in your book. The Debug menu provides the commands and options we'll use to control the debugger. These functions give us the ability to watch values of program variables change as the program runs, to change these values, and to set breakpoints. Breakpoints are places where the program automatically stops running so that we can see exactly what's going on. The functions available in the Options menu apply to all the elements that make up the IDE. If you're interested in finding out more about them, they're further described in the book. There's one thing that we will discuss in this menu, however. Notice the arrow that follows the Environment command. An arrow following such a command name means that if you select that command, a cascading menu will appear. If we select the Environment command, for example, the Environment Cascading menu or submenu pops up on our screen. This submenu offers several options for customizing the environment. This is a good place to discuss some other environment features that we need to know to customize our environment. Let's select the Preferences option from the Environment Cascading menu. Notice that the Preferences dialog contains 2 kinds of interfaces, checkboxes and radio buttons. The checkboxes are indicated by square brackets. If you select a box, an X will appear within these brackets to show that you have turned on the option that the box represents. Radio buttons, on the other hand, are indicated by parentheses. If you select a radio button, a dot appears between the parentheses. Please note that within any group of radio buttons, only one option from the group can be selected at any given time. Like the Options menu, the commands available in the Windows menu apply to all of the parts of the IDE. They're used for accessing and controlling the various windows that make up the environment. For example, we can use these functions to change the size of the windows and move them around on the screen, or select a different window in the IDE. We've accessed help in a context-sensitive way when we ask for help in the Parameters dialog. Context-sensitive help is similarly available throughout the IDE. The Help window is especially useful when we want to browse the help that's available for the entire system. It allows us to view the contents of the help system and to see an index. To read about any item in the contents or the index, just select the item you want to know about. Because Turbo Pascal's help system is a hypertext-based system, it's cross-referenced by means of links. This makes it easy to get help on related topics. Let's take a look at an example. In Pascal, there's a kind of loop called a for loop. We've heard of it, but don't know exactly how to use it. Let's go to the index and find for. There. One of the really neat features of help is that you can copy code samples right into your programs. To copy such a sample, use the mouse or the cursor to highlight the help text you want and copy it to the clipboard by using the copy command in the edit menu. Next, use the paste command. Then you can edit and compile the program. And now we're ready to wrap up our tour of the IDE with a closer look at working with the editor as a prelude to writing our first program. If you want to start the program so that it opens a particular file, then from the DOS command line prompt, type the word turbo followed by the name of the file you want to open. As you can see, now Turbo Pascal comes up with the card file program in the editor window. That's all there is to it. The Turbo Pascal editor is probably a lot like your word processor. The cut and paste operations make it possible to move text around easily by cutting it from one position in the program and pasting it in at another position. And the copy operation can really save a lot of time when we're programming. To see how, consider the following lines of code from the card file program. Notice that this program repeatedly uses a block of 3 procedure calls: go to XY, write, and WriteLine. It's repeated 4 additional times with different parameter values. We can copy and paste this block to save a lot of time. Then we can use the editor to change the values of the parameters as necessary. We don't want to work on the card file program just yet, but it does offer an easy way to embark upon an important subject that we need to discuss before going ahead and starting a new program. That subject is structured programming. Although you may never have heard of it before, the idea of structured programming is not new. It's been around for a long time, and there's nothing mysterious about it. Turbo Pascal is a structured programming language. That simply means that it's based on a set of rules to help you approach the task of programming in a consistent and methodical way. It allows you to break down a problem in a structured way so that we can solve the problem in a well-defined set of programming steps. And when we say that Pascal is a language, we mean it very literally. It consists of words and a grammar that specifies the way in which the words can be combined. In practice, this means that the elements that make up a program must be entered in the program in a specific order. Before we start a new program, let's use the card file program to show some examples of the elements that make up Turbo Pascal. Reserved words are terms that the Pascal language defines for specific tasks. Reserved words that appear in the card file program are shown in all uppercase letters. The compiler doesn't care about case, but it's a convention we use to provide clarity. Right off the bat, we can see that program is a reserved word in Pascal. Other examples of reserved words include type, string, array, record, procedure, begin, if, then, repeat, until, and end. Words in lowercase, or in some combination of upper and lowercase, are user-defined names, referred to in Pascal as identifiers. Examples of identifiers in the card file program include num of cards and max row. If you try to use a reserved word as a user-defined identifier, you'll get a compiler error. Generally speaking, you should try to use identifier names that are meaningful. That is, they tell us what they're used for. A schematic of the general Pascal program structure appears in this diagram. After the initial program statement, there's a very important part of the program known as the definition section. This section contains the uses, labels, constants, types, and variables that will be used in the program. Uses tells the compiler what other independent program files, called units, are used by the main program. Labels include the labels used to mark places in the program that goto statements will go to. Const includes the definition of the constant values used in the program. It allows programmers to assign easy-to-remember names to the values. The type block is where user-defined data types are specified. Finally, the var block contains the user-defined program variables. The remainder of the diagram consists of procedures, functions, and the main program. These are the sections of the program that do the actual work to accomplish the program's task. The time has finally come to get behind the wheel and take Turbo Pascal out for your first test drive. But first, you need to close the card file window and open a new window for your program. This is easily accomplished by selecting Close from the Windows menu. This step closes the card file program. To open a new program file, select New from the File menu. A new program window opens up in the editor. As you can see, the compiler calls the new program noname.pass, at least for the moment. Since this is your first test drive, it would be appropriate to name the program you will enter Greeting. To do this, just select Save As from the File menu, enter Greeting in the input box, and select OK. Now you're ready to enter the Greeting program. You can find this program in the section of Chapter 2 entitled Getting Your Feet Wet. Once you've entered the Greeting program, save it to your disk by using the Save command in the File menu. And at long last, you're ready to compile your first program. To do this, just select Compile from the Compile menu. If you correctly type the program, it should compile without any errors. If you did make an error, for example, if you forgot the semicolon at the end of a statement, you'd get this error message. It says that the compiler expected to find a semicolon, and notice that the blinking cursor appears right where the error was detected. By the way, the colon equal is known as the assignment symbol. Statements in which it appears are called assignment statements because they're used to assign values to variables. Now that we know what the compiler does when it finds a mistake, let's correct the program and recompile it. Just because a program compiles correctly doesn't mean that it will behave exactly as we intend it to. Let's try it. Great! The program ran exactly as we intended. When a program doesn't work the way we want it to, the debugger is the tool to use to fix it. But we'll be covering the debugger in some detail later on. Learning about the IDE and writing our first program is probably just about enough for now. So here we are at the second major stop in our Turbo Pascal tour, where we'll begin looking at the mechanics of programming in more detail, starting with the subject of data and how it's represented in Pascal. All of the information in the computer is stored as a sequence of zeros and ones. How the computer interprets these zeros and ones depends on the type of data that they represent. They can be a kind of data known as a constant. If they are, the sequence used to represent them does not change. Or they can be a type of data known as a variable. In this case, the sequence, or value, can change. There are 5 basic data types in Pascal: integer, real, char for character, string, and Boolean. In this lesson, we'll cover these Pascal data types and see how they're used to declare variables. We'll also consider how to represent different kinds of numerical information using different numeric data types, and how to convert from one data type to another. But first, let's take a closer look at user-defined identifiers and the use of constants. In the last lesson, we saw that there were several reserved words in Pascal. These words are integral parts of the Pascal language. They have a very specific meaning to the Pascal compiler. We can't use any reserved words as identifiers in our programs. And here are some names of built-in functions and procedures. Although they're not, strictly speaking, reserved words, it's generally a good idea to avoid using these names as programmer-defined identifiers. The online help system has a complete list of built-in functions and procedures. Now that we know what we can't use when making identifiers, let's take a brief look at the rules for making identifiers that we can use. These rules are self-explanatory, but there are a couple of points that should be mentioned. Each identifier must be unique within our program, and it's best to use descriptive names. It makes the program easier to read and to understand, and this is especially important if other programmers will be using your work. For example, a variable called account balance is more informative than a variable called AB, or var1. But be careful not to make identifiers too long. If they are, typing them can get tedious. Now we're ready to discuss some techniques for using constants. Let's begin by taking a look at the constants declaration in the card file program. The first thing to notice is that we assign values to constants with an equal sign only. This is because constants are assigned to values when the program is compiled and can't change when the program is running, which is why they're called constants. Variables, on the other hand, are assigned values when the program is run by using the := symbol. The next thing to notice about these declarations is that the constants are named with descriptive identifiers that aren't too long. The first declaration is even commented for absolute clarity. Now, let's look for some other occurrences of the constant within the program. We can do that by using the find operation in the search menu. So let's find the next instance of the constant. And here's one where the constant is used to set the size of the dec array. Let's find another. The constant is being used as part of a conditional expression. And one more time. Again, the constant is used as part of another conditional expression. The point here is simple. We can make changes to how the program works just by changing the constant num of cards at the beginning of the program. And that's the purpose of using a constant. But there are some things to watch out for. Consider this program segment. When the compiler places a value in a constant, it also assigns that constant a data type. In this case, the compiler will consider constant 1 to be an integer, and constant 2 a real or floating point number. To make sure that we're aware of the type of a constant, the best thing to do is explicitly declare the type, as we see here. Even if we explicitly declare the type, however, we could still run into a problem if we're not careful. For example, if we tried to compile our program with this code in it, a compiler error would result. To understand how the problem arises, we'll turn now to our discussion of data types and variables. As we mentioned earlier, there are 5 kinds of Pascal data types. Each one is represented differently in the computer. In order to prevent errors, Pascal has rules on combining these types, so we don't inadvertently mix them. Let's take a look at how they're stored. The smallest unit of a computer's memory is a bit. Each bit can hold either a 1 or a 0. This means that the computer memory is organized to hold numbers as they're represented in the binary number system, also referred to as the base 2 number system. There are 8 bits in a byte. Binary number representation within the byte is similar to the decimal or base 10 representation we use in everyday life. The lowest order bit, bit 0, represents 2 raised to the 0 power, that is, 1. In other words, bit 0 evaluates to a 0 or a 1. Bit 1 represents 2 raised to the first power, that is, 2. Bit 2 represents 2 raised to the second power, that is, 4, and so on until we get to bit 7, which represents 2 raised to the 7th power, that is, 128. If every bit in the byte is a 1, then the overall value of the byte comes to 255. This is the maximum positive value that a byte can hold. But remember that integers are positive and negative whole numbers. By using a slightly different encoding scheme for the bits in a byte, the byte can hold a range of 255 values from negative 128 to positive 127. As you can see from this table, there are actually 5 different integer data types in Pascal, each of which is capable of representing a different range of values. And here you see how each of the integer data types is represented in computer memory. When we consider this diagram, we begin to see why types are so important in Pascal. The reason is that when we declare a variable to be of a particular data type, we're telling the Pascal compiler precisely how much memory to set aside for that variable. This is true for every variable that we declare. But what do we do about real numbers? That is, those numbers that combine a whole number with a fractional part, such as 3.14159 or 99.95. The Pascal data types used to represent these numbers are collectively referred to as floating point data types. This diagram shows how these types are represented in the computer's memory. All we need to know about floating point types for now is that the real type is large enough to hold monetary values up to 999,999,999.99. This is large enough for most business applications. And now we can see why this code fragment with these constant declarations would cause a problem for the compiler. The compiler does not know how to add two numbers when one is represented in 2 bytes and the other is represented in 6 bytes. Which byte should it add to which other bytes? There's no good way to tell it what to do. So Pascal helps to ensure clarity by what is known as strong typing. In other words, the programmer must be very precise about how Pascal variables and constants are declared. Another of the basic Pascal data types that is frequently useful in programs is the character, or char data type. A character in the standard ASCII set is represented in 1 byte. The term ASCII refers to the encoding technique used to represent characters in most computers. Each ASCII character has 8 bits, so as you might guess, there are a total of 2 to the 8th, that is, 256 characters in the ASCII set. Not all of these characters can be printed, however. Some are used for special keys, like the escape key. Others are used for special functions, like ringing the console bell. This screen shows 2 equivalent ways of assigning the same value. In this case, an uppercase A to a char variable. You can enclose the character to be assigned to the variable in a single quote. Alternatively, you can use the numeric value of the ASCII character. The numeric value is especially useful for the non-printable characters, as we see here. Okay, but if a character is only 1 byte long, what do we do when we need to store words, or even sentences? Pascal answers this question with a powerful data type known as a string. As far as the Pascal compiler is concerned, a string is simply a sequence of characters. A string has some very special properties, however. For one thing, Turbo Pascal has a large number of built-in functions and procedures specially designed to make dealing with strings much easier. By default, the compiler automatically sets aside 255 bytes for any variable declared as a string. But what do we do when we don't need 255 bytes for a string and we don't want to waste space? To see, let's take another glance at the card file program. Here's an example where a string variable has been declared in a way that tells the compiler to set aside only 15 bytes rather than the 255 bytes it would normally use. The last basic data type that we'll cover is the Boolean type. This data type gets its name from the 19th century English mathematician George Boole, one of the founding fathers of computer science. When a variable is declared as a Boolean, the compiler sets aside a single byte. If the variable is set to true, the byte evaluates to 1. If the variable is set to false, the byte evaluates to 0. Note that true and false are reserved words. Boolean variables are primarily used to represent conditional expressions that may be either true or false as the program executes. For example, in a program designed to run a chemical process, it might be useful to know if the boiling point of a substance has been reached. In such a program, we might declare a Boolean variable called boiling point reached. We would initialize this value to false before applying heat, and change the value to true once a certain temperature has been reached. Then the program could use this variable to make decisions that depend on whether or not the substance is boiling. Now we'll conclude this lesson with a brief discussion on converting from one type of data to another. In some programming languages, you can directly assign a value of one data type to a variable of another type. In such languages, the compiler tries to figure out what you mean. Unfortunately, compilers are not yet very good at determining what we mean if we're unclear when we say it, and they can sometimes make mistakes when they try. Pascal avoids these problems by providing a number of built-in functions and procedures designed specifically to accomplish such conversions. For example, the ORD function takes a character and converts it to an integer, while the chur function takes an integer and converts it to a character. There are also procedures for converting from strings to numbers and reals to integers. For additional information on data conversion, please refer to your book. And that about wraps up this lesson in which we've covered identifiers, constants, variables and data types, and data type conversions. By now, you're probably beginning to get the impression that building a program is a lot like building a car. Both have a lot of parts that must be fitted together very precisely. And if that's what you're thinking, you're exactly right. In this lesson, we examine a couple more major parts of the Pascal programs you will write: expressions and operators. Of course, we've already mentioned expressions. In this lesson, we'll go right inside expressions to see how they're put together and how they work. And then we'll move on to operators. As their name suggests, operators are program elements that perform operations. They do things with variables and constants like adding them together. In this sense, we can think of operators as the moving parts found in most expressions. There are several basic types of operators in Pascal, and we'll cover the ones you will use most when you write programs. We'll conclude the lesson with a brief discussion of operator precedence. Expressions are program components that combine data elements with operators and that evaluate to a single value. The card file program is loaded with them. Here's one example. It's pretty clear that this expression evaluates to a number that is 1 larger than the current setting of cardnum. And here's another one. If the variable fstat, which stands for file status, has been set to closed, then this expression is evaluated to false. Now let's take a closer look at the structure of these expressions. Every expression consists of operators, which perform an action within the expression, and operands. Operands are the data elements, usually variables and constants, on which the operator acts. Furthermore, every expression has at least one operator and one operand, but some expressions have more. Expressions with more than one operator are sometimes referred to as compound expressions. The card file program contains a great example of a compound expression right here. Even a compound expression such as this one evaluates to a single value, which in this case will be either true or false. For the overall expression to be true, both conditions must be true. Now that we've seen several examples of expressions, we're ready to move on to a discussion of the operators that make them work. As you can see, Turbo Pascal contains 5 frequently used types of operators. This table shows the arithmetic operators available in Turbo Pascal. Most of these probably look familiar from high school algebra. Notice that this table lists the type of each of the arithmetic operators, either unary or binary. This may sound a bit confusing, but the idea behind these types is really simple. Unary operators are those that take a single operand. Binary operators, on the other hand, take two operands. The two unary operators in this table, plus and minus, tell the compiler the sign of a number. The minus operator is also used to negate the value of the operand. The addition, subtraction, and multiplication operators can be used with integer and floating point numbers. The result of these operations is of the same type as that of the operands. Just make sure that the type of the variable that holds the results of these operations is large enough to accommodate those results. For example, if you add two reals, make sure to put the result in a real as well. Finally, note that there are two kinds of division operators. One for floating point division, the other for integer division. Again, it's important that we correctly match these operations with our variable data types, either integer or floating point, when we use them in our programs. The next major class of Pascal operators is the class of relational operators. The relation operators are all binary. They allow us to compare two operands. These elements will usually be of the same type, but when relational operators are used with numeric data types, integers, and reals, either of these types can be used. Finally, please note that these relational operators all evaluate to either true or false. In other words, in this example, either the two strings are exactly the same as one another, that is, they match character for character, including blank space characters, or they do not. In this case, the equals operation evaluates to false. The same idea applies to all the other relational operators, even with other data types. Next, we come to the Boolean operators. These operators are evaluated in accordance with the rules that Boole created, which are shown here. Since these rules may be unfamiliar to many, it's worth taking a moment now to examine them. Note, for example, that the Boolean AND operation evaluates to true only if the operands on both sides of the AND are true. The OR operator, on the other hand, evaluates to true if either operand is true. Both AND and OR are binary operators. NOT, on the other hand, is a unary operator. NOT is similar to the unary minus arithmetical operator in that it merely reverses the value of the operand with which it is used. Which brings us to the following question. What data types are these Boolean operators used with? Boolean operators can obviously be used with data that is of the Boolean type. Boolean operators can be used with any expression that evaluates to true or false, such as the relational expression we discussed before. In fact, we've already seen a great example of this use in the card file program. Let's go back to it. Notice that in this case, the operands of the Boolean operator AND are themselves expressions that use relational operators. Since each of these relational operators evaluates to a Boolean value, true or false, the AND operator can be used here. The next type of operator we encounter is the string operator. There's only one string operator. This operator is used to concatenate two strings. In other words, it connects two strings together by attaching the end of the first to the beginning of the second, as illustrated on the screen. The operator is called the concatenator and is represented by a plus sign. The last kind of basic Pascal operators, the set operators, will be covered in Lesson 6 on data structures. But there's one more important topic, operator precedence. When more than one operator is used in an expression, in what order should they be evaluated? In this example, it's easy to see that operator precedence is important. We can use parentheses to tell the compiler what order to use when evaluating operators. When you use this technique, the compiler will first evaluate the operators in the inner parentheses. It then uses these results to evaluate the operator in the outer parentheses, as we see here. Well, what happens if we don't use parentheses? The compiler makes an educated guess regarding the order in which to evaluate the operators. This guess is based on the operator precedence rules that are built into the compiler, as shown here. When they appear in compound expressions, operators at the top of this list are evaluated before the ones at the bottom. So if this order is the one you want, you don't have to use parentheses when you're coding compound expressions. For example, here's how the previous expression would evaluate according to these rules. So we didn't really have to use parentheses to get the second result we saw before. However, we recommend that you use parentheses in any case. They make operator precedence absolutely unambiguous, and thus they help to enhance program clarity. And with that thought, we can wrap up this lesson in which we covered expressions and operators, two very important components of Pascal programming. That was close, but that's what I get. After all, this car doesn't have steering or transmission yet, so there's no way to control it. Similarly, our Pascal programs need certain types of statements to drive them, literally to tell them what path to go down. There are two basic types of statements that guide a Pascal program in this way: decision-making statements and loop statements. We've already seen examples of such statements in the first few lessons. For example, we've seen the simplest kind of decision-making statement, the if-then statement, and we mentioned the reserved word for, which controls a certain kind of loop. In this lesson, we'll be covering these kinds of statements in greater detail. Used properly, they give us all the control we need over our Pascal programs. As we can see in this graphic, the decision-making if-then statement has a standard form no matter where it appears or how it's used. Given our previous discussions on Boolean data types and expressions, you probably know that a Boolean expression is one that always evaluates to either true or false. The if in an if-then statement must be followed by a Boolean expression that represents a condition that must be true for the action in the then part of the statement to occur. But what happens when the condition in the if part of the statement is false? We know that the action in the then part won't occur. But what if we need something to happen if the Boolean expression evaluates to false? For example, suppose we decide to enter a road rally. A road rally is a kind of race where the participants travel a predefined course by following a detailed list of rules. Whoever completes the course first wins. Say we want to write a Pascal program that simulates the rally. One thing we'd have to do is represent the rules for the rally in our program. Let's say that the first rule is, whenever you come to a T in the road, take a left if there's a stop sign. Otherwise, take a right. How do we represent this rule in Pascal? Let's just look at how we represent the decision about taking a left or a right for now. Fortunately, Pascal does not require that we use two if-then statements in cases like this. Instead, we can just add another clause to the if-then statement, known as the else clause. This code tells the computer what to do when the if expression evaluates to false. And here we see how that part of the rule can be expressed in Pascal. But how about the part we ignored, the part that said, whenever you come to a T? How do we represent that rule? The Pascal construct to handle that is known as a nested if, and it's shown here in a way that represents the entire rule. We've already declared the functions and variables to allow us to use this structure. In principle, you can nest if statements virtually indefinitely, as illustrated here. But be careful. If statements can be difficult to read if they're nested too deeply. In fact, to avoid this problem, Pascal provides another construct known as the case statement. Here's the general format of the case statement. This construct is very useful when we need to make a number of related decisions. And it's especially useful because it provides a clean way of handling the special cases that could make a nested if statement very messy. The case selector can evaluate to an integer, a character, or a Boolean value. The case list, also known as the case label, consists of one or more constants. When the case statement runs, the selector is compared with each label until a match is found or all the labels have been checked. If we want something to happen even when there's no match, then we can add an else clause to the case statement. Check your book for an example of using a case statement. We've seen how decision-making statements can be used to represent a rule and help us win a road rally. But what if we want to write a program to simulate a speed race? Unlike the road rally, there are no particular turns to take in this case. The cars just go around and around the track, trying for the best time over a particular distance. The decision-making if-then-else and case statements don't help much when the only thing to decide is whether we've traveled the required distance. As you might have guessed, repetitive actions, like a car speeding around a racetrack, are best represented in Pascal by loop statements. Here are the three basic types of Pascal loop statements. Each type is appropriate for a different kind of task, so it pays to be familiar with all of them, even though you may not use them all to the same extent. The simplest type of loop is the for loop. Let's use the debugger to see how it runs. We'll see it step through the loop while we watch the values of variables change. I've used the watch command from the debug menu to add I and running tote as watch variables. We'll use the F8 key to step through the program one statement at a time. The first time through the loop, the computer assigns a starting or initial value to a counting variable, which is also known as a control variable. Then, at the beginning of each repetition of the loop, the computer tests the value of the control variable to determine whether the ending value has been reached. If the ending value has not been reached, the statements that make up the body of the for statement are executed one more time. Note that we don't have to change the value of the control variable in the body of the loop. Pascal automatically does that for us as the loop executes. However, we did explicitly increment the running total variable. For loops are great when we know exactly how many times something must be done, like the number of laps around the racetrack. But what if we want something to happen until a more general condition is met? Recall our earlier example. How could we use a loop that keeps a burner on until the water in the beaker boils? In this case, we might use a while do loop. In this type of loop, a Boolean control expression is evaluated at the top of the loop. The loop repeats each time the expression evaluates as true. In other words, the statements that make up the body of the loop are executed. The loop stops only when the control expression evaluates to false. In our example, we might create a Boolean variable called water boiling and set its initial value to false. With this, we would use a while do control expression that says not water boiling. In this case, negating the false variable means that it evaluates to true, and the loop statements will execute. When the thermometer detects that the water is boiling, it changes the value of water boiling to true. This makes the control expression evaluate to not true, that is, false. When this happens, the loop comes to an end. Don't forget to turn off the flame. The final type of loop that we'll discuss is the repeat until loop. This type of loop is very similar to the while do loop. Like the while do structure, the repeat until loop is open-ended. In other words, it will keep on executing for an indefinite number of times until a condition is met. But there are some important differences between the two loops. For example, in a repeat until loop, the conditional test happens after the first execution of the statements that make up the body of the loop. In a while do loop, on the other hand, it's possible that these statements will never be executed. This can happen if the control expression evaluates to false the first time through. Furthermore, the repeat until loop terminates when the control expression evaluates to true rather than false. Given this, the repeat until loop is probably a better choice for our boiling water scenario than the equivalent while loop, just because there is no need to negate the variable in the control expression. In other words, in this case, using repeat until is logically simpler than using the while do structure. Well, that does it for our discussion of program control. As we've seen, decision-making and loop statements are just the equipment we need to make sure that our Pascal programs stay on track and go where we want them to. In fact, with what we've already covered, you should be ready to try some of the exercises in the book, or even to write some of your own programs. Just go for it! Throughout this tape, we've been using car metaphors because the speed and precision of a high-performance sports car are also attributes of Turbo Pascal. In this lesson, we put a slightly different twist on the metaphor by asking a simple question. Say we want to write a program that simulates a high-performance car around a racetrack. How would we go about writing it? The program will need to make extensive use of on-screen graphics and console input and output. By the end of this lesson, you'll be on your way to mastering these techniques. Keyboard input is one of the easiest ways to provide control to users of our programs. For example, when we run the card file program, it presents us with a main menu that allows us to direct the operation of the program by entering characters. Each of the valid keys corresponds to one of the 5 available card file operations. The card file program also allows us to name files by typing in strings of characters. We can enter numbers to specify how many cards we want to add, and another string to give each card a title. Now that we've seen how keyboard input can be used to direct the operation of a program, let's take a look at how the program gets input from the keyboard. The input function that processes the choice from the main menu is called selectOpt. Let's take a look at the source code to see how the keyboard input is used in the program. Here we see that the standard Pascal readLine function is being called. As used here, the readLine function gets whatever is typed at the keyboard and puts it into the variable called opt. There are several places where the readLine function captures input entered by a user from the keyboard. But readLine is not the only keyboard input function available in Turbo Pascal. Here's a list of the available keyboard input functions. Of these 3 functions, readLine and read are defined in all versions of Pascal. Read key is an enhancement provided by Turbo Pascal for inputting single character data, as implied by its name. This function, along with several other useful I/O functions, is provided in a Turbo Pascal unit called the CRT unit. Let's take a minute to look at what happens when we use read and readLine. Here's a screen prompt requesting that we enter 3 different types of data. Let's respond to this request and see how readLine and read process what we type. readLine reads keyboard input until it reaches a carriage return character. In other words, it reads a line of text at a time. It breaks the line down into values by looking for blank spaces in the line. These are technically known as delimiters. As far as readLine is concerned, the only delimiters are the space character and the tab character. When readLine reaches the carriage return character, it stops. If we had typed in 2 values instead of 3, the program would simply wait until we entered the 3rd value. This is because the readLine call had 3 arguments. The only real difference between how readLine and read work is the way they handle the carriage return. Whereas that character means stop to readLine, read treats it as just another delimiter, equivalent to the space and tab characters. And from the perspective of console I/O, they work identically. To display characters in text mode, we use write and WriteLine. If you have a color display, you can change the background and text colors using the text background and text color procedures included in the CRT unit. These procedures work across windows, and they take effect from the point in the program where they're encountered to the end of the program. If you want to change colors back, you have to call these procedures again. Here are the colors you can choose from. We can use the color names as parameters when we call these procedures. But before we use them in a simple program, let's consider a couple more procedures included in the CRT unit: clear skr and delay. By the way, help is always available. If you forget how one of these built-in procedures work, or if you want a quick online example, just press the F1 key for help. The Turbo Pascal command clear is used to erase the screen and start over again with a blank slate. There are two things to note about clear. First, it works by filling the screen with blank characters. The color of these blanks is determined by the background color that we set. And second, after it executes, clear leaves the cursor blinking in the upper left-hand corner of the display. The delay procedure is useful whenever we want to pause the program for a specific period of time. Here's a simple program that uses the write line procedure as well as the text background, text color, and clear procedures from the CRT unit. Let's run it. Could you tell what happened? How about if we add some delay? Say 3 seconds worth. Now we can see what's going on in the program. Delay is also useful if we want to use the sound procedures provided in the CRT unit. This table shows 9 octaves worth of frequencies we can use with the sound procedure. Let's take a look at a program that uses these frequencies along with the sound, no sound, and delay procedures. Notice that we must use the no sound procedure between repeated notes of the same frequency, or they'll all blend together and we won't hear each distinct beat. Now let's listen. Great. Okay, we're ready to move on to the topic of cursor control. Here are the calls as they might appear in a program. Most PC hardware is set up to display 25 lines of text with 80 characters per column. We can use the Go-to-XY procedure to put the string anywhere in this range. For example, this call could put the first letter of the string in the 7th column of the 23rd line. Now let's take a quick look at an elegant little program we can use to center the text. Notice how the center program uses the length string function and the integer division operator in the Go-to-XY procedure call. This calculates the center position in the string and feeds the value directly to Go-to-XY. Let's see how it works. Great! The text is perfectly centered. And that wraps up our discussion of the operations available in the CRT unit. Check out your book for information on functions and procedures we haven't covered here, because now we're going to go into full graphics. Turbo Pascal includes another unit that adds a large number of graphics operations. This unit is called Graph, and to access it, we have to add that name to the uses declaration in our program. This is all we need to do to get the program ready. We'll leave the CRT unit declared in case we want to use some of its procedures, like delay. But we also have to prepare the system hardware for doing graphics. This is known as initializing the hardware. The graphics hardware is initialized with a graph unit procedure called initgraph, shown here. This procedure takes 3 parameters, GDriver, Gmode, and a string that gives the path to the directory containing the graphics drivers supplied with Turbo Pascal. In auto detect mode, the system checks itself out to see what kind of hardware it has available so it can automatically select the appropriate graphics mode and driver path. These are known as the default mode and driver. The driver is the program that actually operates the graphics hardware. Most drivers let you set the resolution of your graphics depending on your hardware configuration. There's one topic left to cover before we can actually use the graphics procedures to draw something. That topic is the screen, or viewport, coordinate system. The boundaries of this system are determined by the screen resolution of the graphics mode we're using. For example, in VGA mode, the coordinate system is defined by a rectangle that is 640 pixels on the horizontal axis by 480 pixels on the vertical axis. As noted before, each mode has a unique screen resolution, but some things are common to all modes. For example, we can always specify a single pixel using integers to specify its row and column positions. In other words, addressing a pixel in graphics mode is a lot like addressing a character position using Go-to-XY in text mode. Not only that, but the position 0, 0 always refers to a point in the upper left-hand corner of the screen. Referred to as the origin point of the coordinate system, all other points in the viewport are specified in relation to this one. In other words, they're specified as a number of pixels away from the origin in both the vertical and horizontal directions. Here's a selection of some of the graphics routines available in Turbo Pascal. Now let's draw some rectangles and circles. We'll use several, but by no means all, of the procedures in the graph unit. The first statement we'll add after the call to init graph is the clear viewport procedure. We use this to make sure that the graphics display is empty before we use it to draw. It works a lot like clear skirt in text mode. The next statements we add are analogous to the text background and text color procedures in the CRT unit. The procedure set BK color is like the text background procedure in that it changes the color of the background used. Set color is like text color. It changes the foreground color. In order to draw several rectangles and circles, let's use a for loop. Next, we'll use the rectangle procedure, followed by a call to delay. Note that the parameters in rectangle specify the upper left and lower right corner points. After delay, we want to add a circle to the drawing. We use the circle procedure to do this. Circle uses three parameters. The first two specify the x and y coordinates of the circle's center, while the third determines the radius of the circle in pixels. Now let's run it. And there it is, our first true graphics program. On the way here, we've covered many of the tools you'll need to create that race car simulator. They're included in the CRT and graph units that Turbo Pascal provides to enhance standard Pascal. If you want more information on text mode input and output, check out Chapter 6 in the book. And if graphics has you fascinated, make sure to look at Chapter 13. With a little practice, you can quickly put the power of graphics to work in your own programs. Oh, hi, it's getting there, piece by piece. I've just about got the engine assembled, which of course relates to the theme of this lesson. You've probably noticed that nowadays when we build something, from a model to a real car, rarely do we go from the smallest individual pieces right to the finished product. Instead, we first put together related groups of parts, or subassemblies like this engine. As we've already seen, the very smallest pieces of data are defined as basic data types: integer, character, real number, and so on. In this lesson, we'll take a look at groups of related data of these various types. These groups are known as data structures, and there are two kinds of them: static data structures and dynamic ones. We'll talk more about the dynamic ones a little later. This lesson covers the static kind. There are many types of static data structures: sets and enumerated types, arrays, and records. By the end of this lesson, you'll be familiar with all of these. And even though we've already introduced strings as a basic data type, we'll talk about them a little more in this lesson. So, without further ado, let's talk about the set type. In mathematics, a set is a collection of items. Each item in the set is called an element of the set. In Pascal, all elements of a set are of the same data type. The data types we can use to make sets are Boolean, char, and byte. Here's some code for defining, declaring, and initializing two Pascal sets. One set is called evens, the other odds. Though these sets contain different elements, they're both of the same data type. In this case, the programmer-defined type digits. Note the statement defining the data type digits. The two dots between the 0 character and the 9 indicate that this type is defined by means of a range. Because all the data types that can be used to define sets, booleans, chars, and bytes, are ordinal types, you can always use a range to define set types. The only limit is that the integer value of all the set members must be between 0 and 255. That's why sets cannot have the broader range of integers as elements, even though integer is an ordinal type. Here's another example that uses ranges to define and initialize sets called uppers and lowers. These sets contain only alphabetic characters. They're subsets of the full set of characters. And here's some code that shows one way to use a set. We defined a set containing all the upper and lowercase characters of the alphabet, and we use the set operator in. In returns a true if the value of the variable is in the set. Otherwise, it returns false. In this example, the set and the set operator are used to ensure that the input is valid before proceeding with processing. There's one more thing to note about sets. The order in which elements are listed doesn't matter. Here are three equivalent ways of initializing the set of even digits. It doesn't matter which of these you use. In fact, you could initialize the set with any permutation of these characters. Any operation on the set will behave the same way regardless of how the set is initialized. Pascal also has an enumerated type that lets us symbolically define anything as a data type just by naming the things of that type. For example, say we want to write a program to help us keep track of our sports car collection. We can define an enumerated type, sports car, in which we enter the names of each car in the collection. Let's say we have a Jaguar, a Corvette, and a Porsche. Types defined as enumerated can hold up to 65,536 elements, so I have plenty of room to expand my collection. Here are some more examples of data defined, declared, and initialized as enumerated types. This type is known as enumerated because the Pascal compiler assigns an integer value to each member of the list. The assignment is made in the order in which the compiler encounters the name of the type element, starting with the value 0. In the type workdays, for example, Monday is assigned a value of 0, Tuesday a value of 1, and so on. Pascal also includes a number of functions designed especially for use with enumerated types. And here are some examples of how these functions are used. There are several things to notice here. First, whenever we want to use the position, that is, the integer value of an element that is part of an enumerated set, we use the ORD function. And if today equals Monday, the pred function would return an undefined value, since Monday has no predecessor in the enumerated type. Likewise, if today equals Friday, the successor function would return an undefined value for the same reason. Finally, notice that the last and first functions take the name of the type rather than a type element as a parameter. These functions return the last and first elements, respectively, of the enumerated type. Now let's move on to talk a little more about strings. Strings are particularly useful for dealing with data composed of groups of characters, like the feature list of a high-performance sports car. And like enumerated types, strings come with a set of special functions. Here are the functions provided for use with strings. Strings can be used as named or unnamed constants. When a string constant is declared in the const declaration section of a program, the string is a named constant. When a string is placed in single quotes and processed directly as a parameter into a procedure, the string is an unnamed or literal constant. Strings can also be used as variables. When they're declared as we see here, the amount of memory allotted for the string equals the specified size of the string, in this case, 70 characters or bytes. If no size is specified, the amount of memory allocated to the string automatically defaults to the maximum string size, 255 characters. Here's how the compiler stores a string in the computer's memory. This string was declared with a specified size. And here's a little program that demonstrates the use of string variables and one of the special string functions, the insert function. This function takes the string variable, or constant, named as the first parameter, and inserts it into the string variable named as the second parameter, starting right before the position specified by the integer value contained in the third parameter. The integer value passed to the insert function by the third parameter can be specified as an integer value, a named integer constant, or as we see here, an unnamed literal integer constant. Here's what the program will write on the screen. Check out your book for more information on using the special functions to process strings. If we could look inside the compiler, like we can look inside a model engine, we'd see that the string data type is just a special kind of another, more general data type known as an array. Strings are really just arrays of characters, with one special detail. The length of the string is stored in the first byte of the array. There are also more general arrays used for other types of data. We can think of arrays as numbered collections of memory bins. However, unlike the character string array, in general, the bin numbers do not necessarily begin with 0. And the size of each bin is determined automatically by the type of data the array is declared to contain. For example, in this integer array, the size of each bin is exactly 2 bytes. This is twice as big as the size of the character bins in the string array. Pascal handles the details of sizing the bins for us. Here are some examples of arrays declared with basic data types. The price array has 10 data bins, labeled 1 through 10. An array with only one range, like price, is called a one-dimensional array. You can access the elements of the array like this. The model array, on the other hand, is declared with 2 ranges. Each range used defines the values along one dimension of the array. The model array is a 2-dimensional array. Since the first dimension has a range of 3 and the second 10, the total number of data bins in this array is 3 times 10, or 30. You can think of it as a table of rows and columns, like a spreadsheet, with 3 rows and 10 columns. This array can hold a total of 30 different model names of sports cars, with up to 10 model names for every brand name. To access elements in a 2-dimensional array, you need to specify both the row and the column. Here's an alternative way of declaring the model array. In it, we substituted an enumerated type for the numeric range. You can always use an enumerated type for a range. The number of dimensions in an array is virtually unlimited. Since there's quite a bit of data associated with each model, we might want to use 3 different arrays, one for the model name, one for the rating, and one for the price. We can think of these as parallel arrays, since each array has the same indexing. For example, here the indices Porsche 1 refer to the same car in model, rating, and price arrays. Therefore, we can use the same indices to assign values to variables that all relate to this car. In this case, it's our day-use car, the Turbo Porsche. As we've seen, each of these arrays can hold a total of 30 values, with up to 10 for each of the 3 car brands. But what do we do if our collection ends up with 17 Porsches and only 3 Corvettes? If this turns out to be the case, then the arrays we've defined won't be very convenient places to store the car collection. We need a more flexible data structure so we can group the data together better. Pascal has another data structure, called a record, that lets us do just that. Each record is made up of one or more fields. Each field can be of any data type, including user-defined types. Here's a sample definition and declaration using records. Note that we use the record type we defined to create an array of records. This array can contain a record for each car in the collection, up to the limit we set, in this case, 30. We can refer to the fields in a record using dot notation. Using an array of records is not only more logical, it's also more flexible, since we're not limited to 10 cars of each brand. To allow more convenient access to a record's fields, Pascal provides a special statement, the with statement. By using the with statement, you don't have to repeat the record name each time you refer to a field. The with statement is shown here, used in the body of a procedure that initializes the collection array of car records. Of course, even if we have less than 30 cars, if we use the code here, we'll have to initialize all 30 records in the array. The for loop requires it, so we may prefer to code this using a repeat until or while do loop. And with the with statement, we conclude our tour of static data types. Sets, enumerated types, strings, arrays, and records. We've discussed them all, and we've seen that they are Pascal subassemblies built from basic data types. In the next lesson, we'll be discussing two more types of Pascal subassemblies: programmer-defined functions and procedures. In the last lesson, we talked about static data structures and compared them to subassemblies in a car's engine. Now let's make the analogy a little more specific. If we think of those data structures as major engine subsystems, the carburetor, the alternator, and the radiator, then we can think about functions and procedures as the internal moving parts that make the whole thing go: the pistons, the valves, and the crankshaft. We'll take a look at calling functions and procedures, also known as routines, and passing arguments between them. Then we look at how to write these major program components from scratch. We'll talk about global and local variables, and conclude by considering a couple of methods for passing values into and getting values back from functions and procedures. When we put data structures, functions, and procedures all together, we have all the major components we need to build the engine. That is, to make the program run. And now, I gotta run so we can get this lesson on the road. Here are some examples of procedure calls we've seen in previous lessons. All of these procedures are called by their names. Of them, clear, skr, and no sound are the only ones that are wholly self-contained. That is, the only ones that do not pass information into the procedures when we call them. The remaining procedures all use an argument list to pass values into the procedure. There are some important things to note here. First, position in the list counts. The compiler matches the first argument in the list with the first parameter in the procedure's definition, the second argument with the second parameter, and so on. If you attempt to call a procedure with too many or too few arguments, a compiler error will result. The second thing that we must be aware of when we call procedures is that the data type of an argument in the list matches the data type specified for that parameter in the procedure definition. Pascal is a strong type-checking language, and it doesn't let us use the wrong types. For example, as shown here, the procedure text color requires an argument of the data type integer, and not a string. If we try to pass that procedure a string argument, a compiler error will result. Note that the colors are declared as constant integers in the CRT unit. These argument position and data type matching rules for calling procedures also apply when we call functions. In fact, about the only practical difference between calling a procedure and calling a function is that a function always returns a value, and we have to make some provision for receiving that value. The first two examples shown here both capture the value returned by the function in a variable of the appropriate type. In the last two examples, however, the values returned by one function are immediately passed as parameters to a second nested function. In both cases, the return value is fed directly into another computation, so there's no reason to store it in a variable. Now we're ready to get into more detail about creating your own functions and procedures, starting right at the top with the function and procedure headers shown here. The format of functions and procedures has a lot in common with the format of the overall program, as we see right here. This figure shows the format of any programmer-defined routine in Pascal. Like the Pascal program template we saw in Lesson 1, procedures and functions may have sections containing const, type, var declarations, a section containing the definitions of programmer-created routines, and a section that represents the main body of the routine. The major difference between this and the program format is that a program begins with the keyword program, whereas a routine begins with either of the words function or procedure, depending on the type of the routine. So you can think of procedures and functions as self-contained mini-programs inside your large program. In the previous lesson, we saw the body of a routine that we could use to initialize our car collection inventory program. Here's the procedure, complete with the header and the necessary declaration section in place. A point or two needs a mention here. First, just notice how this procedure works. It's declared without arguments, but has its own var declaration for the variables that it uses internally, more cars and count. More cars is initialized to y to make sure that the loop executes at least once. Count is initialized to 1 to start with the first position of the collection array. As the loop executes, users input data for each car in the collection one record at a time. Each time they enter a record, the count variable is incremented by 1. Once they type any character key other than y, or they reach the max cars limit, the loop ends, and so does the routine. When the procedure is finished, the program returns control to the statement immediately following the procedure call, which can be in the body of the main program, or it can be in another routine. But wait a minute, how does the routine know about the collection array and the max cars constant? The procedure contains its own variable declaration, but these variables do not appear here. The variables that are defined within a procedure, like more cars and count, are known as local variables. They only can be used locally, that is, within the routine. By contrast, the constant max cars and the collection array are declared in the const and var declarations for the entire program. Types, constants, and variables defined or declared in that position are globally available. That is, any routine within the program can access these values directly, without requiring any arguments when declaring them. It's tempting to make all your variables global so that they are available in all routines. But this can make your program harder to understand and to debug. If every routine can access every variable in a program, keeping track of what routine is changing what value is painfully difficult. By contrast, when we use arguments to pass values between routines, the references stay clear and keeping track of them is much easier. So here's a golden rule for any Pascal programmer. You might wonder what we mean by minimum use. Of course, that varies from case to case, depending on the requirements of the program. Let's look back at the beginning of the car inventory program. In this instance, we decided to define globally the principal data structure in the program, the array of records named collection. Why did we make that decision? Like the global constant max cars, we expect the array of records will be used by many, if not most, of the routines in this program. That means a lot of argument passing. But this additional work would be relatively unimportant were it not for a couple of other facts. First, the car inventory program is a relatively short one. Therefore, it isn't all that hard to figure out which routine has done something to change a value in the array. As importantly, the array is purely car-related data. It does not contain any information defined in the program strictly for use of the program. Variables used by the program for program control are especially dangerous when declared globally. So under the circumstances, the global declaration of the collection array variable makes sense. If the circumstances had been just a little different, however, we would probably have passed the array from procedure to procedure to make the program easier to maintain. This brings us to the last topic for this lesson, which concerns how we pass arguments between procedures. So far, all the examples of passing arguments, like these we see here, have used the technique known as passing by value. And we've seen how passing arguments can make life a lot easier when it comes time for debugging. This technique is great for one-way exchange of information. That is, for passing information into a procedure or a function. By passing a value to the called procedure, the value is copied and used by the procedure as it performs its task. But what happens if we want two-way communications between procedures? In other words, what if we need to pass a changed value back to the calling procedure? The pass by value technique doesn't help much here, since the routine is working on a copy of the variable and not the variable itself. Instead, we use an alternative technique called passing by reference. Here are a couple of sample declarations in which this technique is employed. The procedure declared here returns the record for the highest priced car based on a record it receives as input. With this technique, the record itself is used in the procedure, as indicated in the declaration by the use of the keyword var. In other words, when we call by reference, if the value of an argument is changed by a called procedure, the variable itself is changed. Which about does it for this lesson. Now that we've covered all the major subassemblies in Pascal, we're ready to take a look at packaging them for use by other programs. Hello again. I found this on my desk. I wonder what it is. Now we're going to be talking about units. Units provide a way that we can package related code, constants, variables, data structures and procedures into coherent entities that can be shared among many programs. Used this way, units can streamline the act of programming and the programs themselves considerably. They help us avoid solving the same problem over and over and keep the code for a program's main task uncluttered with the code necessary to perform auxiliary tasks like user interface management. Units also make debugging and maintenance a lot easier. Once a unit is debugged, there's generally no need to revise it further. And if we do need to revise a unit, we can often change it without affecting any other code. We'll be talking about defining, implementing, and compiling units, and using them with main programs. We'll also look at some more of Turbo Pascal's built-in units. Let's start with the format of a unit. The first thing to notice is that the unit format contains three reserved words that we haven't seen before: unit, interface, and implementation. The reserved word unit is analogous to the reserved word program. It provides a name, that is, a unique identifier, that applies to all the code that follows, and that forms part of the interface to the outside world. So whatever name you specify here is the same name you'll enter in the uses section of any program that accesses this unit. The interface reserved word and the text that follows provides exactly those parts of the code that are accessible to other programs. These parts include, for example, constants and variable declarations, along with those procedures and functions that we provide for public use. In other words, these are the parts that we wish to make available to other programs. It's important to note that this section contains procedure and function declarations, or headers, only. For absolute clarity, these include the appropriate keyword for the type of routine, any arguments the routine takes, and, if the routine's a function, the data type that it returns. The actual code making up these program structures, including any local or private variables that they use, is contained under the last reserved word, implementation. Any functions or procedures declared in the interface section must be defined in the implementation section, or a compiler error will result. The implementation section may also contain private procedures and functions. These routines are not accessible to programs outside the unit. One last point. If we want, we can initialize the values of a unit's variables. When a program calls a unit, Turbo Pascal automatically runs a block of initialization code, such as we see here, between the unit begin and end statements. The position of this block of code is analogous to the main part of a main program. It consists of a begin-end block containing a number of statements that will be automatically executed when a unit is initialized. The unit initialization section shown here is for a command processing unit in your book. This unit could be used in a variety of applications, not the least of which includes our car inventory program. And remember, when we use a unit, all the constants, variables, procedures, and functions declared in the interface section are now available to our programs. We can use them just as if they were built in. That's about all we really need to know to start writing units. Except for one last thing. Units can use other units. If we want to use one unit in another one that we're writing, we need to include a uses statement in the interface section. To compile a unit, select the Compile option in the menu bar. Since a unit cannot be executed by itself, just use the Compile option in this menu. Unlike a main program, we can't compile a unit by using the Run command from the Run menu. When the compiler encounters the keyword unit, it automatically makes a file with the extension .tpu. And that about sums up what we need to know to create our own units. Now, let's take a look at Turbo Pascal's built-in units. There are a couple of important points to note here. First, the system unit is loaded automatically for every program, so there's no need to list it in our uses statement. To use any of the other units, you must add them to a uses statement. And remember, you can use help to see a complete online list of the functions and procedures provided by built-in Turbo Pascal units. And that wraps up our discussion of units. We've seen their structure and should be able to write them in ways that will streamline our programming efforts. And we have a pretty good idea of what the built-in units directly provide. File folders. Well, at least they make the perfect introduction to this lesson, since we'll be talking about files. We've seen how you can create a data structure, like an array, that is capable of holding many records. We've also seen how you can fill up this array by entering data into it on a record-by-record basis, and how records can be added, deleted, or changed. But what happens when the users are finished with our program? They don't want to enter all the data all over again, which means they need a way to save their work. That way is called file input and output. In this lesson, we'll discuss a number of file operations like open, read, write, and close. We'll look at handling errors and accessing record-oriented and random access files. And we'll finish up with a brief discussion of some of Turbo Pascal's built-in file management routines. There are two types of files that we can deal with: text files and binary files. In text files, all data are represented as ASCII encoded characters. Any ASCII character can be stored in a text file, including all the whitespace characters such as tab, line feed, and carriage return. Binary files, on the other hand, are used to store arbitrary data that can be comprised of any Pascal data type, not just characters. This can include the 5 basic types: integer, real, char, string, and Boolean, as well as defined types and data structures, enumerated types, arrays, and records. Most of the time, we'll be dealing with typed binary files. These files are comprised of records that are all of the same type. For example, we could use a typed file to read and write the car records we saw in previous lessons. Untyped files, on the other hand, allow us to access more arbitrary data that we treat as a sequential series of bytes. A Pascal program can open any file as an untyped file. Which brings us to our next subject, the file operations that Turbo Pascal provides for file processing. These routines can handle every aspect of file management. They can be used to assign names to file variables, and to read, write, close, and delete files. They can be used to move around within a file and to detect certain file-related conditions, such as end of line or end of file. Finally, they can be used to manage the file buffer. This is an area of memory set aside by Pascal to facilitate file I/O. Here's how a text file is declared. The file variable is declared in the var section with the reserved word text indicating to the compiler that the variable name refers to a text file. The assign procedure assigns the string that is the DOS file name to the file variable. In other words, it associates a particular DOS file with the file variable used in the program. And here's some actual code that we could use to initialize a text file. Note that if the file does not yet exist in the current working directory, the assign procedure doesn't create it. It just sets up the variable. The file can be created, however, by using the rewrite procedure shown here. But be careful. If rewrite is used with an existing file, it deletes all the contents of that file. Reset and append are used with existing files. Later on, we'll see how to make sure the file does not already exist before we use the rewrite procedure. Reset opens a file and sets the file pointer to the beginning of the file. Append, on the other hand, opens a file and sets the pointer to the end. So generally speaking, append is the procedure we'll use when we want to add text to a file. Pascal provides the close procedure for closing a file. And although Turbo Pascal automatically closes all open text files when a program is terminated, good programming practice suggests that we shouldn't rely on the compiler to do our jobs for us. We should always explicitly close files that we open. Once we open a file, we generally want to read from it or write to it. We've already seen the read, readline, write, and writeline procedures, but there's a difference here. Notice that these procedure calls use a file variable called myFile. This variable has been initialized with the assign procedure and now refers to an actual DOS file which can be read from and written to. When a file variable is not specified, Pascal automatically reads from the console or writes to it. Another way of saying this is that the console is the default file for all I/O. When we're reading from a file, we have to be extra careful about errors. Because Pascal is strongly typed, when input data fails to match the expected type, a runtime error results and the program is terminated. To avoid this, we should be very careful in our I/O code design. If an error occurs while reading a file, we should always report that error to the user, as we see in the following code. Here's a sample program from the book. There are a couple of important points to note. First, the I/O result function is used in conjunction with the reset procedure to ensure that the file specified for copying exists and can be properly opened. If I/O result is 0, the file has been opened. If it's not 0, either the file didn't exist or could not be opened. The second point to note is the use of the $I compiler directive in curly braces, that is, inside a comment. The $I directive is used to turn off automatic I/O error checking so we can report a message to the user. Also worth mentioning is that reset and I/O result can be used to decide whether to use rewrite to create a new file. If the I/O result is 0, then a file of that name already exists. If we use rewrite to create another file with the same name, we'll erase the existing file. As we noted before, a very common form of file I/O is record processing. In this kind of processing, the file is generally manipulated on a record-by-record basis as illustrated here. Here's the card file program to which we've been referring throughout this video. One of the main purposes of this program is to provide an example of processing record-oriented files. The first thing to notice here is the way in which the file variable is declared. Notice that it's file of card, and since the type card is defined above as a record type, it's easy to see that the variable card file refers to a file of records. The card file program uses what's known as a random access file. So rather than just reading the record sequentially, we can jump to any record using the seek procedure. Then we can read the record we want. The card file program provides other useful examples on how to handle record-oriented file I/O, and we've included a copy of the program on your program disk. The file is called cardfile.pass. We recommend that you compile and run this program for yourself to see how it works from the user's perspective. Then you might want to print it out so you can review in detail how this program accomplishes its record-oriented file I/O. But for now, we have to keep moving right on to dynamic data types. Okay, I admit it. This is my real sports car collection. You can't blame a guy for dreaming, can you? In fact, I'll tell you what. Let's imagine that we really do have a great collection of real sports cars. This is a terrific resource that we could be taking more advantage of. So what if we decided to turn it into a money-making operation, say a very high-end car rental agency? We start right off renting cars, but quickly run into a small difficulty. The people who rent them refuse to return them. Pretty soon, we're out of resources and out of business. Well, static data structures are a little like that. They get memory set aside for them that is never released, and computer memory, like our cars, is a limited resource. We can run out of it if our programs don't use it well. Consider the car inventory program. We set aside enough memory to hold one record for each of 30 cars. What happens if our rental agency is successful and our collection increases to 31 or 131? We could keep defining larger arrays, but what if we're writing a program to process a huge amount of data? Setting aside enough memory for the worst case scenario could consume all of the memory available in the computer. If this happens, the program might not run at all. That's why Pascal provides dynamic data types that allow us to allocate memory when we need and deallocate it when we're finished. These types let us use memory, release it, and reuse it as necessary. In other words, it's like getting cars returned so we can rent them again. In this lesson, we'll use a new kind of variable, a pointer, to allocate and deallocate memory and to create dynamic data structures. Using pointers and dynamic data structures is a little extra work, but it's a powerful technique for dealing with large amounts of data. This diagram shows what a pointer is and how it works. A pointer is a data type, and a variable of this type contains the memory address of another variable. In this figure, for example, the pointer variable int pointer is stored in a memory location. The variable contains the address 123. Contained in memory address 123 is the value 42. Because the variable stored at this address is declared to be of integer type, that means the integer value 42. This example shows how we can follow a pointer to access the value of an entirely different variable. It also helps to make another important point about pointers. That is, when we declare a pointer, we must declare it as a pointer to data of a particular type. The type can be one of the basic types or a programmer-defined type, such as a record. In the previous example, we would have declared a pointer to an integer. That declaration is the first in this list. Other declarations in the list are for pointers to other data types. This example shows the declaration for a pointer variable that points to the weekly sum data type. So the variable points to an array type. Note that the caret, or up arrow character, is used to designate pointers. It literally means that the variable is declared as a pointer to the type that follows. Like any other kind of variable, a pointer variable must be initialized before it can be used. Otherwise, it could contain useless data or garbage. In this example, we assign the address of the variable total to the pointer variable sumPointer using the @ operator. We could also have used the adder function, which does the same thing. Sometimes it's useful to have a pointer initialized in such a way that it does not contain a real memory address. This is especially helpful when we're following a chain of pointers and need to know where the chain ends. Pascal provides a special pointer value just for this purpose, called nil. If a pointer has a nil value, it doesn't point anywhere. Any pointer can be assigned a nil value just by using a regular assignment statement with the nil constant. We can also initialize a pointer variable by assigning it to the value of another variable that already has a value associated with it. All that is required is a simple assignment statement. However, to use assignment, both variables must be declared as pointers to the same type, as shown here. We can also use pointer variables to assign contents to the location that the pointers point to. In this example, the pointer variable is initialized to the address of a string variable called message. Then, the pointer variable is used to place a string in the memory reserved for the string, which is located at that address. Notice the use of the caret. When we want to assign a value to the address pointed to by the pointer, or when we want to retrieve a value from the address pointed to by the pointer, we show this by using the appropriate assignment statement with the pointer variable name followed by the caret. If we want, we can use these techniques simultaneously, as we see here. The best reason to use pointers is to dynamically allocate and deallocate memory. This lets us provide memory in our programs on an as-needed basis and recover memory when we're no longer using it. As you might have guessed, we'll use the new procedure for memory allocation and the dispose procedure for memory deallocation. We can use the procedure new to allocate memory for the 5 data types, or for data structures like arrays or records. All we need to do is declare a pointer variable of the appropriate type. Here we see an integer variable being allocated by means of the integer pointer int pointer. Let's look inside the computer to show how dynamic memory allocation works. The computer has a section of free memory that is managed by DOS and reserved for the runtime use of programs like ours. When the procedure new is called, the compiler figures out how much memory is needed based on the data type, and the system allocates that amount of memory by placing its starting address in the pointer variable. In this case, it puts the starting address of a 2-byte block of memory in the int pointer variable. The procedure dispose works similarly to deallocate memory from our program. Dispose returns allocated memory back to DOS for replacement in the free memory area, but the pointer that we declared still exists. To be on the safe side, we should set the pointer back to nil since the memory has been returned. And there's one more point about pointers. This code uses the procedure new with the pointer variable int pointer twice in a row without using the dispose procedure in between. Although this is legal Pascal syntax, doing this can lead to serious problems. Let's see why. The first time we use the procedure new, we initialize the variable int pointer to the address of a 2-byte block of memory used to store a variable integer. We then initialize the value of that variable to 42. Now we use the new procedure again with the same pointer variable int pointer. Another 2-byte block of memory is dynamically allocated by setting the value of int pointer equal to the starting address of that block. We initialize the value of that variable integer to 6. But what happens to the block containing the integer 42? Int pointer no longer points to it, so there's no longer a way to reach it, and we can't reuse it. If our program does this often enough, all the memory could get used up. So here's another golden rule of Pascal programming. If you follow this rule, as you write larger and larger applications with increasingly sophisticated use of dynamic allocation, you'll never have to worry about running out of memory. Which brings us to the last topic of this lesson. We've seen the mechanics of using pointers and managing memory. Now we're going to use these techniques to dynamically allocate larger data structures. Let's start with arrays. Here's some code that allocates an array of reals. After the procedure new executes, the pointer variable distance pointer will point to the starting address in the dynamically allocated array. Then we initialize the first position in the array to 109.3, indicating how far we drove on the first day of the year. And of course, when we're finished, we should dispose of the array. Here's some code that dynamically allocates a record, and then when it's finished, disposes of it. Records can be used to create additional dynamic data structures, such as linked lists. A linked list is simply a data structure composed of records in which each record has a pointer to the next record in the list. The last one has a nil pointer. Here's how the process works. Each pointer points to the next record in the list, establishing a link we can use to reach that record. which concludes all our topics for this lesson. In our next and final lesson, we bring everything together to introduce you to object-oriented programming. So here we are at last, the final stop in our tour of Turbo Pascal. Here's where we put together everything else that we've covered so far to talk about an advanced approach to designing and implementing Turbo Pascal programs. This approach is called object-oriented programming, or OOP. It's an evolutionary approach that takes structured programming to an even higher level to provide easier code maintenance and more reusability. But there are a lot of building blocks we need to know about to make this approach work. In this lesson, we'll be covering object types, variables that declare instances of particular objects, methods of operating on objects, communications between objects by means of messages, encapsulation, the mechanism of inheritance between objects, and polymorphism. Then we move on to how we can create objects from scratch. That's plenty to cover, so there's no time to dally. Object-oriented programming rests on three conceptual pillars: encapsulation, inheritance, and polymorphism. First of all, encapsulation means combining related data, functions, and procedures into Turbo Pascal structures called objects. Object types are just another kind of programmer-defined data type, like records. The second concept is inheritance. Inheritance is a way of creating one object as a descendant of another. Descendants inherit the properties of their ancestor. This lets us create objects based on existing objects and saves us a lot of repetitive coding. The final concept is polymorphism. Polymorphism means many forms and refers to the fact that different objects can respond to a general command in different ways. We'll be seeing concrete examples of what these terms mean as we go along. For example, here's what an object type definition looks like in Turbo Pascal. To use the most precise terminology, the components of an object type, as shown here, are referred to as instance variables and methods. X, Y, num items, and items are the instance variables in the menu object type. The procedures init and display are the methods. It just so happens that both methods in this object type are defined as procedures. A method could also be defined as a function. We can access the instance variables and methods using the familiar dot notation used for records. Calling a method in an object is sometimes known as sending a message to that object, which leads us to inheritance. Say we wanted to create a new type of menu, such as a cascading menu. This menu will work like our existing one, but it's displayed a little differently. All we have to do is define a descendant, or a subobject, of the menu object. A descendant inherits all the instance variables and methods defined for its ancestor, that is, for what we call the base object. Notice that the cascading menu object is defined by the object reserved word followed by the type of its ancestor in parentheses. This indicates that the cascading menu is a descendant of the object type menu object. Cascading menu automatically inherits all the instance variables and methods defined for the menu object type. There's no need to redefine them. Which brings us to the idea of the object hierarchy. Objects that inherit properties from other objects can be thought of as being in a hierarchy. In this illustration, the base object is flying object. One level down in the hierarchy are three different kinds of flying objects: airplanes, birds, and UFOs. The airplane object has a further descendant, a 747 object, which inherits much of its behavior from the airplane object. Now let's take a look at a hierarchy of geometric objects. In this hierarchy, point is the base object, and all the descendants are related in the sense that each is derived from point. A line is formed from points, a rectangle is formed from lines, and a square is a rectangle in which all the sides are of equal length. And now we're ready for a more precise definition of polymorphism. Polymorphism means many forms or many shapes. It's a way of giving an action one generic name that is used by many objects, each of which implements the action in a different fashion. Note that the drawing of the shape is different depending on which object is executing the action. To see what this means, let's go back to our hierarchy of geometric objects. One of the things that all of these geometric forms have in common is that they can be displayed on a computer screen. This fact immediately suggests a method we can use to illustrate the idea of polymorphism. So let's say the action all the objects know how to do is display themselves. Here's what happens when we call the generic display method in each different object. Just as we might have expected, what the display method does depends on which object we're drawing. That's what polymorphism is all about. But display is no ordinary static method. Display is a special kind of method used specifically to implement the property of polymorphism in object-oriented programming. This kind of method is called a virtual method, and we've already given a hint of what we mean by virtual when we referred to an ordinary method as static. Virtual methods are dynamic. This means that unlike static methods, their behavior is not fixed when we compile the program. Instead, the behavior of these methods is only defined right when they're called. The formal way of saying this is that virtual methods are bound at runtime and not at compile time. Binding is the way we associate the generic method call with a particular method implementation. For virtual methods, this binding occurs on the fly. So we can associate virtual methods with different objects on an as-needed basis, and the behavior of the virtual method is determined by the object to which it is bound. To use a virtual method in this way, we must declare it as virtual. Here's some code that does just that. The first thing to notice is the reserved word virtual used with the procedure display. This tells the compiler that it should not associate calls to this procedure with any particular block of code until the program is running. You might have also noticed the presence of another new reserved word, constructor. This is very important because every object that has virtual methods must have a constructor. A constructor is a special procedure that initializes an object before it's used. And just as new had its counterpart dispose, so does a constructor have a counterpart. Not surprisingly, this counterpart is known as a destructor. A destructor is optional, but can be used to deallocate memory or perform other operations when we're finished with an object. One last thing to note, we must always call a constructor before calling any virtual method associated with it. Your book contains some additional examples of object-oriented programming. Once you start thinking of programs as a bunch of cooperating objects, you'll find you can build programs a lot quicker. With that thought, we wrap up this introduction to object-oriented programming. In fact, this concludes our tour of Turbo Pascal. We've shown you all of the fundamental concepts of programming and even a few advanced techniques. I hope you've enjoyed this introduction and that you'll continue to learn and program on your own. You'll find that you can really go places with Turbo Pascal.